architecture that is drift canceling, and that's what makes it unique. Back in the days before synthesized variable frequency oscillators, or VFOs, drift in the first LO of a receiver was a big concern. The frequency stability of a typical Superman style general coverage receiver is dominated by the stability of the first local oscillator, or VFO. Typically, the VFO is tunable over the entire frequency range that the receiver is designed to operate over, and typically operates at a frequency above the receiver's frequency range. So given that it's operating at a high frequency and tunable over such range, making these VFOs stable and with very little drift over time and temperature was a difficult thing to do. The Wadley loop overcomes this problem not by making a very stable VFO, but by simply canceling the drift that might occur in that VFO. I find it very interesting to take a look at some old technology like this Wadley loop and the unique way that it solves the problem, because you never know when you might need a unique solution to a modern problem. So let's take a look at how the Wadley loop works. The Wadley loop is a triple conversion architecture. It may look a little complicated in this block diagram, but it really is quite simple to understand. Let's walk through it step by step. So the front end, we've got our input signal coming from the antenna and preamp and things like that that goes into the first mixer. Of course, driving that first mixer also is our first local oscillator. This is the one whose drift that we're always so concerned about. The output of that first mixer gives us a number of mixing components, and primarily the two that we're interested in would be the local oscillator frequency plus or minus our input frequency. Usually we're interested in only one of those, some are difference, and it's usually the difference. So we're going to use a bandpass filter to give us just the local oscillator minus Fn. That becomes our first IF. Of course, this is no different from any other super-amplified receiver. I should note also that the numbers that I've indicated here for frequencies are the numbers that are specific to the Yaesu FRG7. So we can see, for example, that the first local oscillator is tunable from 55.5 megahertz up to 84.5 megahertz, or over about a 29 megahertz frequency range. So the first IF frequency in the Yaesu FRG7 is centered at 55 megahertz. Now, of course, any drift that is in this first VFO is also going to result in frequency drift coming here on the first IF. So how do we cancel it? This is kind of where the magic of the Wadley drift canceling loop comes in. The same local oscillator signal is also mixed in another mixer with a crystal-controlled oscillator. Crystal-controlled oscillators are typically very stable. In this case, it's a 1 megahertz crystal oscillator. But it goes through a harmonic generator. The harmonic generator takes that single frequency, 1 megahertz output, and outputs essentially a comb of frequencies. At every harmonic of that 1 megahertz frequency up to a little bit past 30 megahertz. So the output that comes here is at 1 megahertz, 2, 3 megahertz, 4, 5, 6, 7 megahertz, etc., up to at least 32 megahertz. All those signal tones, if you will, are present into the other input of this mixer. So now at the output of this mixer, we're going to have essentially the mixing components of the first local oscillator frequency plus or minus all of these tones from the comb generator. So this composite of all these mixing tones is applied through a narrow bandpass filter. In the case of the FRG7, it's tuned to 52.5 megahertz and has a bandwidth of less than 1 megahertz. So what is that going to do? It's essentially going to select just one of those components, one of the difference components between that local oscillator and the comb. Let's look at the bottom of the band, for example, at 55.5 megahertz here. When that is mixed with the 3 megahertz tone, that will wind up with a signal coming out here at 52.5. But as it tunes up, that signal will walk out of this filter, and if we keep tuning the VFO up, then once we're 4 megahertz away, then the 4 megahertz component will come through here. So essentially at every 1 megahertz through the tuning range of this dial, we're going to pass a signal out of this bandpass filter that is at 52.5 megahertz. That becomes our second LO, and we use that to mix with the output from the first IF filter, which creates essentially another set of sonic difference frequencies, this signal right here, plus or minus FLO2. And again, we use a bandpass filter to select just one of those, and what we're going to select is the FLO minus FN, which is essentially our input signal that we're looking for, minus FLO2. That's the signal that appears here. And again, in the case of the FRG7, this bandpass filter is centered at 2.5 megahertz, a bandwidth of about 1 meg. So let's take a look at how this cancels the drift. We take a look at the signal that's here. That's our FLO1 minus FN, so that's the frequency we've got coming in here from our bandpass filter, minus the local oscillator 2 frequency. However, the local oscillator 2 frequency is essentially equal to the VFO frequency minus the comb. We'll put that and expand that equation down here. We just sum all this up. We see that the FLO, the frequency from the local oscillator, drops out of the equation, and what we're left with here is a frequency that is